The last two pieces of elasticity are called the shear modulus and the bulk modulus. What is shear? Well, you're accustomed to the term wind shear, which is basically wind that's perpendicular to the direction of motion the plane is going in, right? And so shear is pretty much the same thing. You've got a force, like on this bookcase, that's perpendicular to the direction the bookcase is made to take force, in some sense. And so if you look at what all these variables are, there's the length of the side against which you're putting some force. There is the length perpendicular to that the bookcase deforms, some delta x. There's the A, this area A, that's the area of the bookcase, a cross-sectional area of the bookcase that's in the direction that you're deforming. So just it's kind of opposite to this one where your cross-sectional area is perpendicular to the direction you're deforming. Here, the cross-sectional area you're talking about is in the direction that you're forming. So you got F over A, and then you've got delta X, right, and L naught. And this shear modulus S is this proportionality constant here. You could rearrange this equation to look a little bit more like the other one, in which case it would be F over A is F over A is S onto delta X over L naught, right? And that makes it look a little bit more like the the Young's modulus equation. So this is our shear modulus. F over A is S delta X over L naught. Just the delta X, the A, these are all, these things mean different things in this, and so you have to keep track of what they mean. The last one we're going to talk about before we look at some values is the bulk modulus. And again, I could rearrange this. Delta V over V is onto B. B delta V over V is F over A. But this has more to do with F over A is pressure. So the pressure on an object um, can uh, can cause it to compress, right? And that's what this is really about, compression due to pressure on an object, or lack of pressure causes an object to expand. And so in aircraft, you worry about the expansion piece, and in when you've got pressure from the inside, you worry about the expansion piece, and in submarines, you worry about the compression piece, right? So kind of opposite problems there. Finally, some values. Young's modulus, all right, 70 times 10 to the ninth newtons per meter squared. You're like, whoa, those are big values. Yeah, those are big values. But let's look at what that means, all right? 10 to the ninth. That means your force per unit area equals 10 to the ninth times delta L over L naught. What that really means is delta L is going to be really small because this number is really big, 10 to the ninth. Why is 10 to the ninth? Delta L is going to be really small. And so typically you don't see enormous changes in normal objects due to this, right? If you have an aluminum rod, you're not going to be able, you can't just take an aluminum rod and grab the ends of it and stretch it, right? And notice that stretch. That's what we're talking about here. You're not going to notice how much it stretches. And so that's why these units seem like, whoa, they're way out there. Well, it's because things don't change much. And so these proportionality constants are large to get at you've got these little bitty changes that are happening on the other side. Bone compression, um, you know, and shear is different for these. This is why you worry about forces that are not in the direction things are designed to be in terms of shear for aluminum. Um, and I think that pretty much gets us there. And I'll get some problems in as soon as I can, and we'll keep on moving.